It's a rather last-minute talk. By last minute, I mean I discovered that I was going to do it at about 4 p.m. today while we were in our office in The Hague. So my name is James Nugent. I work for a company called Event Store, among other things. We build a database for event sourcing, which is why we're going to talk about this. Prior to that, I've worked at a bunch of tech companies, Joyent, HashiCorp, Boundary, Jet.com, all kinds of stuff, applying some of these principles. And so I'm aware that, so I've given this, I did not write this talk between 4 p.m. and now. This is a talk I've given before. And I realized that it has a rather unfortunate title for the Netherlands, because someone informed me that SOA has a different meaning here. And then I checked it on Google to confirm that other meaning. So unfortunately, I did not rewrite it, so sorry about that. The other interesting point is that my laptop didn't really work with the setup here, so I have the notes on here and the slides on here, so it might be a little bit slightly disjointed. So I'm going to try and do a whirlwind tour of all of these things, of service-oriented architecture and how event sourcing fits into that, and then how another pattern called CQRS, or Command Query Responsibility Segregation, fits into that as well. I'm not really going to look at much code, although there are a few snippets throughout the slides. So before we spend time looking at event sourcing or CQRS, I'm going to spend a bit of time putting them in context. And one of the mistakes that was made early on in event source systems, so 2006-07 kind of time, is when this pattern sort of emerged as being a good idea. One of the big mistakes that people made was trying to apply it everywhere in a system. So every aspect of a system would be event sourced, or every component would be event sourced, or sometimes there would just be one component and it would be event sourced, covering everything. So I want to talk about SOA first, SOA, service-oriented architecture. I don't know how old people are here in general, but when SOA was first talked about in the late 90s, I guess, early 2000s, this was one of the phrases that you'd find, like, this was the purpose of it, right? The aim of this architecture was to help align what IT were doing with what a business were doing. Right? And the way it got adopted was companies that had tools that didn't do SOA would write articles in seatback magazines for major US airlines about how everybody should be adopting SOA. And then they should be adopting their tools. And naive CIOs and CTOs would sit in these planes flying around from place to place in the US. They'd read them and say, oh, everybody appears to be doing SOA. We better do that too. And that's what caused it to be adopted. And the problem is, if you look at what became of SOA over the first few years of its life, it's hard to see how it came back to this objective, right? So let's go back for a while to, was anybody here building systems in advanced COM or something like that in the late 90s? A couple of people. OK, cool. So let's think, a stereotypical architecture of a system from the 1990s. Right? We had a client, usually a MFC app, or occasionally something, maybe Java or something like that, talking to a database. And the database had all of the logic in it, and lots of clients, like everybody's terminal, would connect to the database, and that's where all the work would be done. And people realized over time this doesn't really scale very well. Right? As the number of users increases, this doesn't actually work that well. And if you want to expose it to the internet, then this really doesn't work very well. So what ended up happening was we added an extra layer in. Right? We called it a business logic layer. And this would run on an application server, abstract the database away, and the clients, which could now be some kind of web app, or maybe by this time probably a WinForms app or something like that, would talk to the business logic layer, and the business logic layer would talk to the database. And then this is kind of the state of the art for the three-tier system was kind of the state of the art in the early 2000s when SOA became a thing. So having been through this transition, what people did was say, well, clearly the thing we're going to do here to do SOA is add another layer called services, right? So our services are just going to sit in front of the business logic layer, usually do exactly the same thing as them, and then just proxy calls down one layer extra. So now you have a bunch of extra XML, because it was all XML then, running through your system, and nothing really improved. So if we look at this, it's kind of hard to see, how does adding this extra layer here help achieve alignment between what your business wants and what IT or development wants to do? So the problem with this term service is, you can look at it like this and say, well, obviously we just add an extra service layer and there's no problem. But the problem is, what is a service? And to be useful, we have to have a common definition of service. And service is like the most overloaded term in the industry. And apparently is even worse for non-native English speakers, because it also has another meaning which is completely disjoint in English from the meaning of the word as we're going to use it in technology. So, in particular in the US, you go to a restaurant and you have a server who serves you or gives service to you. And that doesn't really help us for achieving IT business alignment, because it has nothing to do with it. So let's see if we can do a better see if we can try and dig into what service actually means so that it can be useful in achieving IT business alignment. So in the Microsoft space, the way that people started with SOA was this crazy-ass keynote by this guy called Don Box at PDC in about, actually, so Dave there used to work at Microsoft at this point, I think. Don Box, a distinguished engineer at Microsoft, or maybe a tech fellow at Microsoft at this point, gave a keynote about how SOA was going to work and defined these 4 principles. He actually gave it, sat in a bathtub on stage, like actual roll-top bath filled with water, gave his keynote in the bath. Cool. Yeah, and it was certainly interesting. But he basically defined these 4 tenets of what it means for an architecture to be service-oriented. And if we go down, they all sound like obviously good and actually sort of relatively self-evident things, right? So services should be autonomous, and they should have boundaries that are explicit, and we don't want to be sharing binary artifacts among them, but instead contracts, and that we don't want to hard code the way these services talk to each other. We want some kind of policy that controls that. And these are all obviously good things if you just think through them. But if you go back and think how the WCF or the Java equivalent of WCF, whatever that was, like adding a service layer helped achieve these, and think them through for a minute, well, it does the last 2 okay. If you have a WCF service, for example, sure, you share like a contract and you don't necessarily share a DLL between them. And actually the policy stuff is really good. It has lots of configuration points about how a service talks, the transport for it, the security around it. That stuff is great, but the first 2 are a problem. If I have WCF service A and WCF service B, and as part of serving a client, service A calls service B, can we say that service A is autonomous? And the answer is clearly no, because if B is down, A can't serve its clients anymore, so A has a strict dependency on B. And the other problem is, although there's a clear boundary at the front door, there's a clear contract at the front door of a service, there's nothing that really says what it can do from there. So it's kind of like having a front door but no sort of walls or roof or anything. So what we're looking for really is a definition of service and service-oriented architecture that uses something different than inserting a layer of web service calls in our application architecture. And there we go. Cool. So this is the definition, for want of a better one, that I'm going to use throughout the rest of this talk. So a service, as I'm talking about it from service-oriented architecture's perspective, is going to be the technical authority for a specific business capability. It's kind of a broad statement, but let's think about what it means to be a specific business capability. So if you're going to be a technical authority, not a business capability, let's look at what it means to be a technical authority for something. So if you're going to be the technical authority for something, you have to be able to make decisions. So what that means is that all the data and the rules that you're using to make those decisions have to live within a service. Right? So if I have a bunch of reference data in a database and a service, some kind of application function that makes a decision based on that data, from a logical perspective, the data in the database and the logic in the function are part of the same service. because they're part of being a technical authority for a particular capability. And so the corollary of that is, once you've divided your business or your architecture up into services, there are no pieces left over. So it's not a layer in an architecture. It's something which encompasses every aspect of the architecture. So before we look at some examples of what might be services in this model, let's look at what are definitely not services in this model. So a service that only has functionality, only has logic in it, is not it's a function, it's not a service. Right? So if you have something that's stateless and just adds two numbers or calculates sales tax or something like that, it's not a service, it's a function. Whether you wrap it up in XML over RPC, or whether you call it via a WebSocket, or whatever, whether it's wrapped up in some kind of a React component or whatever the hell people want to do with them, logically, in an architectural sense, it's a function and not a service. And furthermore, a service that only has data and does CRUD operations on it, or writes or saves it or whatever, is also not a service, it's a database. Now, functions and databases are obviously part of software, and they're things that we have, but if we call them services, then the word service becomes meaningless, and we can't use it to refer to any sort of larger construct which is more meaningful. So if we go back to that article, to the original definition that we had, and look at what we were doing commonly in those 90s, early 2000s, mid-2000s systems, what we weren't doing was building a service-oriented architecture. What we were doing was building systems of functions, calling other functions, calling other functions, calling databases, which is clearly not very efficient. There's a view of software published in a paper from 1996 by a French author called Philippe Cruchat, whose name I probably just butchered, sorry for anybody French here, which specifies that what you can do is separate any software system into lots of different perspectives. So you can look at the same project from lots of different people's perspectives, or lots of different perspectives within, from logical perspectives. And the architecture of each of those doesn't need to be the same. So it separates things into a logical view, which is where are the logical business boundaries of these components within a system. It separates it into a development view, so where does the code for each of these live? Which source code repository does it live in? Which Visual Studio project or solution does it live in? It separates it into a process view, so when this software is deployed, who's responsible for each aspect of the process to get a particular component of the system deployed? Who has to QA it, who has to press OK on the release process, something like that. And finally, it separates it into a physical view. So when you're running on physical servers or in a cloud, what's the deployment topology as opposed to the development topology, or the logical topology, or the process topology? Now, one of the things that's commonly been done recently is to couple all of these together. And if you couple all of these things together, what you get is microservices. Right? You get one repository that leads to one release process, that leads to one type of physical server running a particular process, or maybe one Kubernetes pod or something like that, which represents one logical function of the system. But that's not the way it has to be. You don't have to do that. You can instead tease these things apart and gain flexibility from being able to address each of these in a way that suits a particular organization. The paper is called the 4+1 architectural view model. The +1 is the fact that all of these things are bound together by use cases of a system. So you have a particular path through a system, and for that path, you should be able to identify this is the logical components involved, this is the where the code lives, all that kind of thing. And this is actually kind of useful to us, because if we take our other definition of service, the wrong way. I really dislike this clicker that I borrowed from Dave. No, no worries. The buttons are like, there's 3 buttons, firstly, and it's like the bottom one doesn't do anything. So many services, so what we're going to end up with, if we separate the logical, services live in the logical tier of our 4 views of architecture, right? These are the top level decomposition of our system into components. An application is more of a development or process or physical view, and it's kind of up to the company as to exactly where they fit. So what we can end up with is a single application that consists of components from lots of different services. So many services can have components deployed in the same application. One is a one is a lower level composition container, and the other is a logical grouping of things that go into an application. Oh, again, the wrong way. So what we often end up with is seeing services as being vertical slices and containing components throughout the traditional layers of a stack. So they're vertically cross-cutting instead of horizontally cross-cutting. So to use a, wrong way again, I'm just going to keep my finger on the down button and hope I don't move it again. We can, for example, see that if we were in an e-commerce situation, we might have a marketing component of user suggestions, which has some UI associated with it, and uses one particular strategy for the back end. But we could choose to use a completely different back-end technology for the UI components in a different service relating to the product catalog. But all of these things would be deployed together. The UI would probably be deployed into some kind of website that's doing composition somewhere, either on the server or at the client. This is not an accidental example, because one of the original people that did SOA, sort of by fiat, and discovered a lot of these patterns was Amazon.com. The reason Amazon.com did SOA is not because they looked at the tenets of SOA or saw Don Box's keynote or anything like that. It's because Jeff Bezos sent an email to every senior manager at Amazon saying, you need to be doing service-oriented architecture within 6 weeks, and if you're not, you're fired. So within 6 weeks, they all figured out, well, what does SOA, how does it benefit us, what can we do with it, because otherwise we're fired. So probably different teams had different takes on it, all to say that they were able to do it. But if we, maybe I got rid of that slide, sorry, hold on. Okay, sorry, I cut a few things out to try and keep this down. I don't want to talk about that for a second. If you look at this page from Amazon.com from a few years ago, this is the domain-driven design book, which covers a lot of concepts about domain modeling. You can clearly see that different aspects of this have different ownership models, depending on which responsibility of the business or which capability of the business contributed the data. Right, we have some stuff that's very static. We have a picture, title, some reviews maybe. They're all clearly product catalog information. We have the particular price that's being extended to me. That's clearly not the product catalog, because not everybody has the same price for every product. There's something else that knows for a particular product, this is the price that's extended to a particular user. And then down here, it tells me how quickly I can get it, and based on where it knows my shipping address is, my default shipping address, and whether or not the thing is in stock. This is clearly also not related to the product catalog, right? There's a shipping domain somewhere that's calculating, if he orders it now, I can send this to this person within 5 hours and however many minutes. So what we end up seeing is that applications become a composition of components which live within different logical services. So our logical view of the architecture is completely different from the physical view or the development view of our architecture. And what we start ending up with then is composite applications, which and there's some choices to be made as to where they compose. But that's effectively the real principles to help you actually get to the point where service-oriented architecture can help with IT business alignment. So there's another statement of this, by the way, of the 4+1 architectural view model. And it's become, again, more popular recently as people have discovered it talking about microservices. And it's a law from a mathematician and computer programmer, computer scientist called Melvin Conway, who observed, I have a story about that in a second, but who observed that organizations building systems tend to build systems which exactly mirror the communication structures of the organization themselves. The best example of that is if you have 4 teams building a compiler, what you will have is a 4-pass compiler. Right? Everything will go through a stage developed by one team, because that's how the communication structures of the organization go. Services map very neatly onto that because business capabilities tend to have internal communication paths that are separate from the external communication paths in those organizations. Mel Conway is, this paper was published in 1968. Actually, I recently had dinner with him in Boston. He's still working and still alive and still working. He started at IBM the year that my father was born, which gives you an idea of how long he's been working on this kind of stuff. And still doing interesting research and publishing interesting papers, which is nice. So, what I want to talk about briefly next is a pattern called event sourcing. I'm not going to dwell too long on this because Chris is going to talk about it afterwards, but event sourcing, as it fits into an SOA, it's not a top-level architecture. Right? You can't take a business and say, we're going to do event sourcing here, and then start writing code. Right? There's some decomposition required because you only use event sourcing in particular areas of the system. So if we go back to our no, that one. If we go back here, we might choose to use event sourcing for user suggestions or for inventory, but not for other aspects. Right? You're going to apply it to some small, it's a pattern that should be used within a particular service. So, what is it? Has anybody here heard of event sourcing in the past? Cool, okay. So for those who haven't, I'm going to try and do a fairly basic introduction to it and try and keep it fairly quick because Chris is going to go into a lot more depth shortly. Who here uses an ORM for their system? Entity framework, NHibernate, still, anybody? Cool. What's the other one? Java, what's the main Java one? Hibernate, JPF, something like that. There's even one in Rust now called Diesel. So here's a question for you. If you have an ORM, who decides what transaction goes into your database? Is it the programmer? Is it the user? No, it's the ORM, right? The way an ORM works is it loads a row from a table or a few different rows. It puts them into an object model. It keeps a copy of the object model. It gives you another one back to mutate. And when you're done, you call save. And it compares the copy it kept and the copy that you gave it back, mutated, and works out, well, what SQL transaction do we need to run to get the database to match this object model? Is it always correct? Has anybody ever looked at the code base for NHibernate? Was that fun? There are a lot of code, right? NHibernate is tens of thousands of lines of code. You sure it's correct? And the answer is it's definitely not correct. Entity framework may be a bit more correct now, but that had its moments early on as well. Sorry? They do have unit tests, yeah. I believe, does NHibernate even have tests? I don't know. Yeah. It probably does. Okay, cool. Here's another question for you. Who here has an audit trail in their system? Cool. So if you have an audit trail in your system, if everyone that had an audit trail in their system can put their hand up again. Okay, keep your hand up if you can prove in a courtroom that your audit trail is correct. Cool. That's a very common response, right? So if you can't prove it's correct, what's the point in having it? Like, it's a lot of work for nothing, right? In particular, if you have an audit trail based on an ORM, then not only can you not prove it's correct, you probably also can't prove why. And in the kind of systems that require an audit trail because of regulation, that's a problem, or it can be. So the fundamental point of event sourcing is, or one of the fundamental points, or the original point, was to solve those two problems. Right? The reason it came about in the modern day, it's not a new pattern by any means. It was in use since if you look at like an IBM mainframe, the entire system works by event sourcing. But in the modern, since 2005, 6 kind of time, the reason it came about was for financial transactions. We're building algorithmic trading systems and needed to be able to prove that what the system said it did is exactly what it did, because these things were playing with real money in the market, and they were very, very fast. And if you put something in the market that's playing with real money very fast, you can lose a lot of money very fast. And you need to be able to know, why did this happen? Who do you fire today? And how do you make your money back? Right? So the fundamental revelation of this was not that, or that. It was that state changes in a system need to be an explicit part of a model. So an ORM makes them very implicit, right? You go and you take an object, you mutate it a bit, and then you say save, and your state changes whatever change was derived. But actually, if you're trying to model a system to say exactly what happened, what you should probably do is make these state changes an explicit part and name them. So instead of doing that, instead of doing what we do with an ORM and deriving state changes, instead, we capture the state changes in an object or a business entity as a series of events. So events are things which state something that happened. And specifically, I don't know if Dutch has this, but specifically something that finished happening in the past. So French has le passé composé for expressing these things. So it's this thing that finished happening in the past. And that can lead to some awkward constructions. But here's some examples. So an event is an account was promoted to gold status. Another one is the application was submitted for approval, or the credit check failed. These are all things which have finished happening. They're facts about a system. And if you know all of the facts about the system, then you can use them in interesting ways to derive the state of a system. So let's look at an example. This is my favorite example because I used to work for a big e-commerce site, not Amazon. Everyone could imagine modeling a shopping cart in a relational database, right? So you'd have your cart, and you'd have some line items, an object model of them. You'd have the cart, you'd have some line items, you'd have some shipping information, and you can see how you'd map that onto a relational database, right? You'd have a cart table, and the cart would have customer ID, and then the cart would have a one-to-many relationship with the line items in there. And you probably have an item ID and a quantity for each line. And that's one way to look at it, right? This is a structural model of a shopping cart. It's not the only model, though. A different model would say what we're going to do is look at the events that caused a particular cart to get into a given state. So instead of saying, wrong way. Instead of mutating this table and say, we change the quantity of socks in my cart down from 5 to 3, and just updating this quantity field here, what we're instead going to do is keep a record of the events that led us to get to that state. So we're going to keep a record of, well, we created our cart, and then we added some shirts, and then we added some socks, and then we removed a shirt, and then we checked out. Are these two models equivalent? They're not, actually. So they look superficially equivalent, right? But there's a subtle difference, which is in this model, I don't know why I'm pointing it at the screen, it's not going to work any better there. In this model, we're mutating a static state, right? So if we remove an item, we're just updating the quantity and saying, well, now we have 1 instead of 2. In this model, we retain a complete history of exactly what happened at which point. We can rebuild this model by replaying all of these events and saying, well, if we see we added an item, we're going to go and put that in the table. If we remove an item, we're just going to update the quantity and set it to 1 minus. So we can use this to derive the structural model. Now, in fact, we'll see we can use this to derive any structural model, not just a table system. But actually, we've lost information in the other one. Because we've gone and mutated something, you can't recover all of the lost data, right? This added 2 and removed 1 is something that disappears in that model. Now, there are ways of doing temporal databases that don't do that. I'm not discounting those. They work in some places quite well. But they're a much more complex model than just retaining a list of what happened. So if we can create a structural model by replaying these events, then storing the structural model anywhere in our entire system is just an optimization, right? Instead, we could persist the entire domain model just by keeping that list of events that happened. And it tends to be that mature industries have this as a foundational principle. And particular mature domain models already do this by default. Who has worked on accounting systems before? Or is anybody here an accountant? Okay, cool. Oh yeah, I forgot that. accounting works like this naturally, right? You don't update the state of your bank account and say, set the value equals $50. You maintain a journal of all the transactions that got it there so you can verify it's correct. Also that you can go and run different transactional calculations over it to discover a different model based on the same transaction history. It's how fraud analysis works, for example. So I'm going to skip over most of the code here because we don't really have time for it, but in fact, I'm going to skip over all the code here. There are plenty of examples of this online. There are some frameworks to help you do it as well. But so who here would consider themselves a functional programmer? F# programmers, anyone? Cool. So in functional terms, event sourcing is really simple. It's like a one-liner. It's the current state of an object is a left fold over the previous behaviors. So what does that mean? Where are we? Okay, I'm just going to wing it and see. Actually, so we can go further than that. We can project any structural model, right? So when we looked at it before, we were going to project back we were going to replay the events and build our structural model from the list of events. But actually, there's no reason in principle we can't also go and build a star schema for reporting. Right? It's common in enterprise systems to find that you throw away all the data that you need to go and build a reporting database, and then you rederive it from the crappy data you actually kept. If you keep all the events, you can use them to build lots of different views into the same data because you have a complete set of exactly what happened and why. It also solves the audit trail problem. If you need to be able to prove exactly what happened at a given point, write it to write once media, and suddenly you can't go and change what happened in a system. You can't have the situation where the operator goes in and changes the bet just before the winning horse comes in. A real system with a real story behind it, which can be talked about over beers later, maybe. Okay, it also has a dramatic impact on testing. So who here tests their system? Cool, everybody, right? So who tests that their system does what it's supposed to do? He does, okay, cool. I have a different question though, and that's, cool, that everybody does that. Who also tests that their system does nothing it is not supposed to do? That's a much harder problem, right? You don't go and look at every database row after you run a unit test to prove that it hasn't changed. Event sourcing changes the nature of programming slightly, because you don't have side effects all over the place. It makes it a much more functional approach, and business logic becomes much more like pure functional programming. So let's look at some example tests with this. What every test becomes is, for an object, given the past behaviors of the object, so the events that have happened in the past, when we call this particular method or when we do this particular operation, then we get some other events out of it. And more importantly, or as importantly as these are the events we get from it, that we don't get anything else. So if we decouple the downstream effects of a system, the effects from the decision to make the effects, we can test that the decision was correct by asserting that only the decisions that we wanted were made. And that makes the testing problem much simpler, because it isolates the testing to being testing the downstream effects of something separately from testing that the correct decisions for those downstream effects to happen were produced. I also had some code in here, but I'm going to ignore that too. These are actually, that's worth looking at. It's worth noting that several of these, a particular method doesn't have to correspond to one particular event. So in this particular case, a particular action or a use case of a system, we're going to record a complaint from the subject of a particular review. That can result in multiple different events being emitted which affect different services in a system. Right? We can say we're going to emit an event which is going to remove it from remove a particular review from the internet, and we're also going to use that to kick off the arbitration process for determining whether or not a particular review is any good. That I'm going to kind of skip over testing for the most part for the rest of that. That leads us to a problem though. If all we have is a sequence of events, how do I run this really simple query? And if all I have is my million shopping carts, each of which is represented as a sequence of all the things that happen to those shopping carts, how do I find, and this is it's not something you'd likely want to do, I might want to do it, how would I find all of the shopping carts where the user's name begins with a J. So what you do is you'd replay all of the events for every shopping cart, right? And then you filter them all. That's a really terrible way of doing it. It's very inefficient. In a relational database, this is a solved problem, right? Because it's something that relational databases are really good at. On the other hand, if I want to determine the connectivity of a graph-structured data, so I want to find the cycles in the list of products that people added and removed, so that I can identify clusters where people are looking at the same sort of products and substituting one for another, then I probably want some kind of graph database instead, because that's what they're really good at. You can't query event streams directly except for one particular type of query, which we'll talk about. We probably won't talk about, actually, but it exists. Temporal correlation queries. Querying event streams is really good for that. So the problem with querying is you can't query the event streams because it's really inefficient to replay them every time just to get the result of every query. So there's another pattern that you can use for this, which is called command query responsibility segregation. It's an acronym that really rolls off the tongue, especially if you're not a native English speaker. So it was shortened down to CQRS in about 2006-07 kind of time frame. The problem with CQRS is if you look at where the keys are on the keyboard, for years and years, if you Googled for information about CQRS, it used to say, "Did you mean cars?" I had a major victory the other day when my iPhone auto-corrected the word cars to CQRS instead, which was like a full circle thing with this, like 15 years later or whatever. And CQRS is a pattern which gets a lot more attention than it deserves. Right? It's not a complicated pattern. It doesn't imply anything except that we service reads in one way through one code path, and we service writes through a different code path. It doesn't say we have to service them from 2 data stores or anything like that. Who here reads from views in their SQL database but writes into tables which materialize those views? Right? It's a pretty common pattern. But that is effectively CQRS, right? You're servicing reads from a view specifically designed for the read, and you're servicing writes through a table model which is optimized for writing. And actually, we can't service every type of query that we want via one model. A SQL Server database or a graph database or Cassandra or DynamoDB, they can never service every type of request that you're going to want to do. So you're always going to want other data stores that have different views of the same data in them. And the common example is a star schema from something like Redshift or a data warehouse in some kind of form. And the great news is if you do event sourcing, then what we can do is apply the left fold that we used to apply to get the state of a particular object to derive read models. And you can derive lots of them from the same events. So what we can do is we can take the transaction log of all the events that have happened in our system and play them into different sources through different functions to get the benefits of each one of these specialized read models in the particular area that's going to be best at. So we could have a document database for serving our UI, a graph database for cluster analysis, and a star schema for arbitrary reporting. And the problem with that is we need to put all this stuff together, right? We have to orchestrate it. So the common way to do that, if you think about the view around a system, is we'd have a domain model, which is now producing events. And we'd write the events into an event store. And we'd also write them out to a queue. And the queue would read all the messages and run the fold function and write into a SQL table. And then our client can query through a thin read layer that doesn't have to have an ORM, right? It could just be like linked to SQL or even just like select star from whatever to make its reads. There's a slight problem with this, which is what happens if you want to drop your projection. So you decide, oh, I now need this new view of the data. I need this extra table. And what you want to be able to do is go back to the beginning of time, replay everything from the beginning of time, and construct this new model with all of the pre-existing data in it. So one way that you could do this is have 2-phase commit between whatever queue you're feeding into your denormalizers and your event store. That is one way to do it. So 2-phase commit, everyone's familiar with, like a DTC or something like that. Who's operated the Microsoft DTC at scale? Anyone have fun with that? Does anybody ever wake up to the emails that says a transaction is in doubt on your coordinated transaction system, the state of your system is unknown? So the way to solve two-phase commit, so the problem with two-phase commit, right, is a system that says, okay, let's say your database 1 and your database 2. So I'm going to say, I want to write this, prepare this write. Okay, you say fine. I say to this other guy, prepare this write. He says, okay. And then I say, okay, well, we know these two can do the write. So now I'm going to say, okay, you commit and you commit. So the problem comes in the last phase, where if this database is committed but this one hasn't, then we don't know what the state of that system is, right? He could have received the commit message and then gone offline having done the work, or maybe the message got lost on the way, so now they're in an inconsistent state. So the solution to this is a different protocol called three-phase commit. It's actually not the solution to it, because all you do is defer the problem. So I once worked on a production system where we released a version of the software. Yeah, a little bit over, but this one's worth a slight diversion. We released a version of the software overnight with one minor bug fix. The next morning, and it was a tiny bug fix, like a typo in the UI. The next morning, every single operation in the system had 50% extra latency on it. Every single operation. And people spent days and days going through every aspect of the system trying to work out why it was slower. Because now transactions were timing out. And no one could figure out why. So then we deployed the old version with the typo again, and it was still 50% slower. Okay, so it's no longer the software, it must be the environment, right? So started talking to the admins and was like, well, what else happened around this time? He said, well, I got an email the other day saying your transaction is in doubt because of two-phase commit. One way you can fix this is to go and check the box that says enable three-phase commit. So I used the outage time during the upgrade to go and do that. So now, instead of prepare, prepare, commit, commit, every transaction is prepare, prepare, acknowledge, acknowledge, commit, commit, or 50% more round trips around the network. So, of course, they still fail at the end. So, well, now there's more points they can fail, so it's even worse. So that doesn't solve it. The solution here is to not have two separate things that you have to commit to at once. Instead, what you need to do is use an event store that you can write through and subscribe to. So you can write events into it and have subscribers hung off the back of it that will say, you know, when something gets written, this is going to get notified about it. And that way, if I want to throw all this away, what I can do is say, I know events, up to events, from time 0. And then they'll get notified about everything from the beginning of time. Or I want to know about events from 30 minutes ago because I just restarted, and then it can just replay events from 30 minutes ago. So that's how you put it together, and that's what a stereotypical CQRS system ends up looking like. There's a problem with this, right? If you're not doing everything transactionally anymore, you have to deal with this thing called eventual consistency, right? If every database isn't being updated synchronously with each other, then it can be the case that this database is out of sync with the facts in this database. And I don't really have time to talk about how you solve that, sorry. It can be solved in almost every case. There are some strategies for it. I'll put these slides up, and then these are some ways. So as a quick summary before I hand over to Chris, event sourcing and CQRS, they're patterns to be used in the small, inside a service. They're not top-level architectures. They're tactical patterns, not strategic ones. Event sourcing as a pattern stores the state of business entities. Instead of storing the particular state at a given point in time, it stores a history of all the decisions that were made to get to that point. And then, in order to be able to query those streams, you need to apply this other pattern called command query responsibility segregation to take those event streams and denormalize them into models that you can then query in whatever way you find optimal. So I realize I ran quite a bit over. So at this point, I will not do questions right now, but I will be around for at least these 2 cans of beer's time, and can have questions afterwards. So at this point, I guess we'll hand over to Chris, who has a much deeper dive into event sourcing specifically. So thanks for listening, and actually, I guess, since Chris is... thank you.
there's a lot of information about how to build event source systems, what event source systems are, that conflicts in the market today. And there's a lot of people who are confusing event-driven applications with event-sourced applications. So I just wanted to go over 7 core principles that when you're building an event source system are going to help you succeed, right? A lot of these are taken from places where I've seen people trip up, event source systems haven't worked well, and the successes where I've seen good event source systems and how they work. Because when they're put together properly, they can be very powerful and very successful. So here they are. 1, and this seems a little bit odd, but make sure what you're doing is actually event sourcing and not something that looks like event sourcing. Ensure global order. Invariants, only use the stream. This is very similar to microservices. As soon as your services need other stuff, you get trouble. Fine-grained streams, right? You don't want to replay the world every time. Optimistic concurrency, that lets you be deterministic that the world hasn't changed underneath you while you're busy thinking about something, all right? No flags, no nullable data in your events. We'll get into that a little bit deeper later. And commit as you go. So let's get into the details here. Making sure that you're actually event sourcing. So my take on event sourcing is a rather literal version of it. Event sourcing says you derive the state in your application from a history of events, right? So if we look on the right here, we're showing 2 different types of discrete autonoma, right? Effectively, we really have a fancy version of a Turing machine. If we see our event stream as a tape, where we write down the symbols, and then we read them back, make a decision to decide whether or not to write something out to the tape. The main difference is we're accepting input from the user, right? And we make a couple other constraints where we're saying we're doing append only, right? That's fundamentally what we're doing with event sourcing. There are a lot of people that talk about saving all of the commands in a series, saving all of the inputs, and that's their version of event sourcing. The problem you have with that is now without the state machine, right? And that state machine is different between version 1 of your project and version 2. Every time you release the software, what's in that state machine changes. So if I need version 1 again to understand it, I either have to make that state machine understand every single possible variation from the beginning of time for all the commands, or it's going to give me a different result when I replay it. And the business hates that. If they run a report once, they get one number, they run it again, they get a slightly different number, they're going to lose their mind, right? So I want to make sure that that same machine produces the same expected result and allows me to change that result upon request. If the business decides that this series of events now means something different, if I'm event sourcing, I can do that. If I'm doing credit card monitoring and I change the window for late payments to say if I see 1 late payment in a month, you're fine, to I see 1 late payment in 15 days, that can change credit scores even though the facts remain unchanged. We want to be able to do that between version 1 and version 2. The other thing I see people doing all the time is that private state on the right, they save that out. Again, I can't understand that state without an exact version of that machine. I can't take a new version and run it and get the new expected result. I also can't do time travel. I can't say, well, what if we had done a better job and then run against my historical data and find out if I'm right. If there's a new report that we need, I can't run that report on all of my historical data and get a new answer. Because normally if you have a new report and you're using a traditional database, the day you started, you get 1 day of data. If you're using event sourcing and you come up with a new report, you can have historical data on that report back from the first time you started recording data. Right? So we want to make sure that the history of events, the history of your business changes are what you're basing it on. And there was a really good question about DDD and events, because we are doing something a little bit dangerous here. We're saying that we're going to write down an immutable event log of what happened. And as time changes with the business, what we recorded is all we have, right? So Eric Evans said one of the concepts he wished he'd gotten into the Blue Book was domain events. You know, business changes. That's the model we want to be thinking about as we record these events and updating our application history is domain events. And we want them to be as close to what happened as possible. Because using that domain language gives us the most stickiness to the way the business thinks about the problem, the way they're going to change their thinking about what they're going to do next. So if we have domain events in our event log, it's going to be the most robust for changes. It's going to be the easiest to write new reports, to create new features, because we're talking and thinking like the business. All right. So just on the right here, this is a state machine for accepting input and writing into the log. On the left here, we have a state machine, which is reading the log and creating all those projections that James just covered. So the view here could be SQL table, you know, a document in a document database, a view in your system, a graph. It's whatever you need. So just two different types of state machines. Ensuring global order. So you'll see I've got the same slide all the way through, because this one slide can answer all of these questions. So again, in a lot of systems, we don't have a guarantee as we're logging things to a stream or to different streams that the order will be the same between them, right? So if we look at something like you're writing into a data center here in Europe and you're writing into a data center in America, generally you'll get a local ordering, but there's no global ordering between them. Inside your application, how often or how important is it going to be for me to rerun the report? And the truth is you can basically accept you're going to have to rebuild downstream, aka derived state from your primary source. It's going to happen. There's 3 reasons it'll happen. It's going to happen because you have a fault in the system. You have a database, something's going to go offline, eventually you're going to have to rebuild it, right? The second one is the business is going to change their mind, right? You know, you go back to the example of credit reports. If the business changes their mind about what the facts mean, then you're going to have to restate the reports. Now that could be because the business had a correction. They're like, oh yeah, no, I put that in wrong, we got to change it. Or they could just say, our interpretation of this is now different. We know more now. And the third one is something no one likes to admit, defects. We're going to have defects in these, and we're going to have to correct them. And when that occurs, we're going to have to replay. Now, there are ways to optimize that by taking snapshots and understanding how far back you have to go, right? So the next one that I see people getting trouble is invariant checks that must use the data in the stream. So what I mean here is in the state machine that's doing the writing, when I'm evaluating a command, which is a request to record something or change state in the system, right? We need to have certain rules the business wants us to keep. We want those rules to be evaluated based only by the events in the history for that system. So we want it to operate as a microservice. Because if we don't do that, and we have the state machine, for example, using some downstream states, you're going to find all these long loopbacks and race conditions and unwinds and performance problems and bottlenecks, right? And while this is sometimes a difficult constraint to deal with, it also answers one of the biggest questions I've always heard: how do I decide what's an aggregate? How do I decide what's a microservice, right? The answer is this microservice aggregate stream writer has to be autonomous. It needs to own all the data in the stream, and it must be able to answer questions about it, right? And so you divide them up until you can do that. And that's how you know how big those aggregates, microservices, stream writers need to be. That's how you make them autonomous. And you find out, you break things out into finer levels. Does that make sense? All right. So this gets us to the next piece. When we're doing event sourcing, we don't want these state machines to have to run over days and days and days of data, right? We actually want what we need in the state machine to be fine-grained. And these fine-grained streams are logical subdivisions of the master log. So in the top log you see here, we have a master sequence number, and in each of these substreams, there's a local sequence number. So they're logical subdivisions of the master ordered stream, right? Because James was wrong about one thing, at least one thing. There's two queries that a stream database is very optimized for. One, time queries, time window queries, and second, getting a stream of events out, right? But we want to give it a nice targeted set of events for us to recover. This allows us to rehydrate these state machines very quickly if we need to, right? We don't want to be going back over everything. So if you think about it, the event log at the top is your entire database. Don't think about one of these state machines running against, say, your account table. You want to think about the state machine running against one account ID. So you want a stream per instance for everything, right? It owns just this instance. That's going to give you a fast recovery time. It's going to be easy to cache it live in memory. It's going to be easy to recover it, and you're going to be very performant, right? And that's one of the things that's going to make the event sourcing work very well. You can also, if you need to, because these are logical streams on the master log, you can also create other targeted virtual streams, especially for your read side. Here, you can create a stream by event type. You can create that stream for the entire category. Suppose I want to have some read model that's just churning on all of the account createds, right? That's all it cares about. It doesn't care what kind of account it was. Any kind of account that was created, it wants to know about it. And the view here is perfectly valid for that not only to be a SQL server or a database, it can also be producing events. It can say, I'm going to watch these transactions, and when I see this pattern, I'm going to produce a new event, which is fraud alert. or a new event which is gold customer status reached, right? So we can do cross-cutting concerns across all of the streams. And that's one of the reasons why it's actually reading off the master log or a targeted stream, right? This also gets into separating out your thoughts about the read side and the write side. They are completely decoupled in the system, and that offers a lot of opportunity. Optimistic concurrency. So you'll notice here that when I'm writing to the stream, I'm not just appending to the end of the stream. I actually want to write position 6, right? Because most systems we're running, most microservices, I want microservices because they're small, they're easy. I want them to be highly available. I don't want to run just one. Most likely, if I have this account service out there, it's going to be able to hydrate any account instance, run an operation on it, and write it back into the database, right? But what if I have a transaction on the same account in 2 different services, right? I don't want the system to say, sure, we'll put them both in, no problem, right? Think about if you had 2 transactions racing for your account, one of which is an ATM withdrawal for $1,000, and the other which is lock my account, because you just realized that your card was stolen. You want one of those to succeed. Ideally, we want the account lock to succeed first. But what we need in the system is deterministic ordering, right? We want to make sure that if I'm going to write to position 6, that's because I have events 1 through 5 in my history. If there's an event 6, I don't know what state things are in. So I want to throw an optimistic concurrency exception and not allow that write. And that state machine can then read event 6 and check it. But this allows the race conditions in a highly distributed system to be resolved at storage. What's written on disk wins. So if you turn the power off, you turn it back on, you've got a known state. And your SLA is, if it was written on disk, it's there. If it was not, then your transaction did not complete. And James's picture where we say we go through the store and then we report is about this principle. What got committed is what considered to be the record. Following that principle saves a whole lot of grief. No flags or nullable data in events. This is one of the biggest warning signs I see for teams that have not fully understood the power of event sourcing, right? Because as soon as you have flags or nullable fields in your event, you don't really have an event. You actually have multiple events you've folded into one, right? Who here has ever done object hierarchy and table as a storage pattern, right? You take all of these objects, any one of them will fit in this table because you're folding them all together. And so you have nullable fields, sometimes it's this, sometimes it's that, right? Because we've fully separated the 2 sides, we don't need to do that. We can actually do table per type. Why doesn't anyone ever do 4th normal form? Because it's a huge pain in a relational system to start doing all of those additional joins. Here, we don't have them. Here, we're subscribing to particular events and topics, and we can actually subscribe to the top level type for all of those events and get any one of them for something that needs it, or subscribe to just that targeted event for the things that need that. So now it's very easy to deal with type per table or 4th normal form. And you also think about what it means if you're downstream. That means that every single downstream system in your application needs to understand how to unwind this event that's really for events, rather than just subscribing to what it cares about. So you're taking the logic of the writer and you're combining it with the logic in your readers, as opposed to making your type system clear, sane, and subscribable. Commit as you go. So, distributed transactions. One of the things that we've said is we're going to have microservices. Things are going to be isolated, right? You only have your knowledge. That means that more and more, to get a business function done, you're going to need to commit across multiple microservices, right? And as we were just talking about, the more you lock, the more you do distributed actions, the more you're going to entangle yourself, slow yourself down, and then you're going to say, well, why don't I just put this in Mongo? Why don't I just, why am I going through all this? There's a fancy name for this, which is a write-ahead log. But really what it means is that when I'm looking at a business process, that one service cannot commit directly, right? I need to interact between multiple services. I write down my intent. So if it's create user, my event is just going to be user created because I own the users and I'm fine. But if I'm like, say, in a trading system and I've got the block of orders and I want to make a placement, but I don't know if the broker is going to say yes or no to the placement, I don't create a placement here. I say placement requested because that's what happened. Then I process that placement request to the broker system and it attempts to finish the placement. That means the broker system will tell me whether or not that placement occurs. That allows me to do my distributed transactions in a committed fashion. So if at any point you turn off the power, when I turn it back on, I can tell that I'm not in a valid state. All I need is a simple DR process to say, hey, do I have any requests that never finished? I can also have on that an SLA. If a placement has been requested, it should either have an indication of further processing or a rejection within this amount of time. So I can just have another read model watching that transaction process. It becomes a very simple pattern to have a watchdog just saying, well, anytime you see these two things out of bounds by SLA, raise an alert, tell someone, take an action. That way, I don't have to be watching. It's one of the ways I can watch all of my subsystems. It's also one of the ways you can mitigate things like eventual consistency. You just set an SLA and you report on things that expire. So, keeping to these 7 principles as you build your systems will put you in very good stead for success with event sourcing. These are the key things I see time and time again. They either help you or in some cases force you to make the right decisions and face the right problems up front. Make sure you're actually event sourcing. It's not change data capture. It's not taking snapshots. It's not recording commands. Ensure global order, because otherwise you're going to get to a report or you're going to get to a replay and life is going to suck. Invariants are in the stream. Use the commit as you go pattern to bridge those individual streams. Use fine-grained streams because you need that speed and isolation. It also, by the way, fine-grained streams and keeping your invariant checks local, make your unit tests simple, easy, fast, deterministic. They reduce your cognitive load in understanding the system tremendously. and you can start to get provably correct. Optimistic concurrency. Just turn it on, make it work. It allows you to distribute, to run at scale, and still be safe. Flags or noble data are a sign that you haven't actually modeled the business intent of the change, right? You're going back into a developer mindset. The other thing about commit as you go that I like to talk about is when people think about sagas or distributed transactions, they're actually, in my mind, more of a developer IT invention. Because what are we saying? We're actually saying if all of these things don't occur, we're going to unwind all of them as if none of them occurred, right? Whereas in actual business terms, in most cases, something has occurred, but it didn't finish correctly. And having a conversation with the business about what happens when that doesn't finish is extremely profitable, both for you and for them. One of the best examples that I got from Greg years ago was delivering snowplows. If you're in Montreal, you manufacture snowplows because Canada uses a lot of them, but you sell them into the US. You have an order, you process the order, you start delivery, your snowplow is in New York, across the border, 1,000 miles away, and the city that bought it cancels the order. Something went wrong with the purchasing process. Are we going to unwind that? Are we going to suddenly say, nope, the truck never left the yard. That order was canceled, truck's in the yard, we don't have anybody stuck in New York, right? So that's a grand scale, but that's the concept of committing as you go, right? The truck did leave, the driver is in New York, raise it up to a user, ask him what to do. I'll bet you that salesman will sit down and he'll find a different city that wants a snowplow like that or close enough for a discount. And he'll get that sold. But that's not something the software can do. Our job is just to record what decisions were made and help the business do their job. All right, so that's all I've got. I try to be a lot faster than James. I hope I succeeded, balance things out here a little bit. And I do have time for questions.
Typically find as the biggest barriers to entry for guys, for dev teams looking to use event sourcing?
The biggest barrier to entry is that mind shift to a series of business events is what you've got to be thinking about and using those state machines and getting away from the magic of the relational database. So the relational database is awesome in its ability to like pause time, change everything, and then start time up again. And getting away from that to having this really like third, fourth normal form concept of what changed, what do we need to keep track of. Because one of the sidelines there is in the state machine, that private state should be sparse. It's only the things you need to check a new command. If that data isn't used, it should be passed through. It comes from the command, it goes on the event, it goes in the stream, and then the read model deals with it, right? That separation and working through a couple examples, following that pattern, and once you make that mind shift, one of the standard saws is only event source the things you need to because of the barriers. Once you and your team understand it, that's the barrier. Then event source everything. Right?
Just one more thing before I pass this on is just in terms of infrastructure.
Yep.
So, I mean, you mentioned a lot of things, I'm just thinking in terms of transactional guarantees around the different, things getting pushed onto queues and all that kind of stuff. Just in terms of that, what are the barriers there? I mean, typically that's quite a fair amount of infrastructure that's required.
The first thing I would say is use a database, all right? Either use something that runs on SQL, Oracle, or Event Store. Don't use a log, don't use a bus, because that's where you're going to get the optimistic concurrency. If you go with something like Event Store, which is a dedicated stream database, you'll get your fine-grained streams, but you need those semantic capabilities, And then once you're past your core database, then use whatever you want. And then understand also the difference between your application and the rest of your system. Because there, you get into the thing between your private schema, like in a database. Would you ever let another app read your private schema? So don't let any of your private events out. Use a reader to create a public set of events for external consumption, and those are what go on Kinesis or Kafka or the Azure Service Bus. Does that help?
Yep, absolutely.
Yeah, second answer to that as well. Actually, not to that one, sorry, to the first one about barriers to entry. Actually, the biggest barriers to entry that I've found for teams is, there are two things. The first is that there's a lot of documentation about this kind of thing, but most of it is wrong and leads you down a bad path. And that's something that needs to be fixed, and actually we're starting to try to fix that from Event Store's perspective. It causes us a lot of problems because we have customers doing things which are which lead to infrastructure problems down the road, and so we're actively trying to fix that now. That's going to take a while because there's so much bad information. And it comes from sources which are otherwise credible, and they are describing patterns which are valid patterns. They're just not event sourcing.
Right. Yeah, event-driven architectures are fine, but they're event-driven, not event-sourced.
Yeah.
Command sourcing is very useful for disconnected apps.
Yeah.
It's not event sourcing.
Right. There's a bunch of stuff that's that's disconnected, but is still related. The second thing is actually a connection to, or an attachment to object-oriented programming without understanding what object-oriented programming is. So actually, here's a question for the room. What are the two key principles? There are two key principles of object-oriented programming. What are they?
What's called high cohesion, low coupling.
Damn.
Okay,
Yes,
well,
they are.
Yeah.
So the two that everybody says normally are inheritance and polymorphism. And polymorphism is trivial to get rid of because as a foundational principle of object-oriented programming, because it's clearly not. Is C an object-oriented language? No. What is standard in? And the answer is, well, it depends when you connect, right? It might be a file, it might be a TTY, it might be a printer, it might be a modem. That sounds pretty damn polymorphic to me because I can just write to this thing and yeah, sure. So if C can do it, it's probably not a foundational principle of object-oriented programming. And the other one is encapsulation. Sorry, as well as inheritance, people aren't coming up with. Encapsulation is another one. Like, okay, how do I encapsulate in C? Well, I just don't put whatever I don't want other people to see in my header file. And if we ignore buffer overruns for a minute, which is hard to do, but we'll ignore it for a second, that sounds like I can encapsulate pretty well in C, which again means that it can't be a foundational principle of object-oriented programming, because other things do it just as well. Like the principle of object-oriented programming is exactly that. It's that you want private state to you want to present a boundary to the world into which you can send out of which come messages for other things. And if you look at something like Erlang, that's much closer to object-oriented programming as it was defined by Alan Kay, and which is a useful definition, than something like C with classes, which most of the object-oriented programming languages in use today actually are. The other, so Alan Kay posted on Hacker News recently. There was clearly some 19-year-old JavaScript programmer, nothing against those, but who was posting about why this guy's answer on the internet was wrong about what object-oriented programming was, and the guy's response was, "I am Alan Kay." Well, okay, shut down that argument. So Alan Kay defined Smalltalk in the late 70s.
Yeah.
Zero to part, so yeah, late 70s, early 80s, I guess. And so does anybody ever programmed Objective-C? Objective-C, like you'd use for iOS, or you would have used for iOS a few years ago, is the closest relative to Smalltalk still really in use. In Smalltalk, you didn't call methods on objects, you sent messages to objects, and the method call was late bound. And so according to Alan Kay, the definition of object-oriented programming is late binding everything and sending messages. And that's a definition that I'm willing to take on the basis that he's the one that invented it. And if you think of business objects in that form as things that receive messages, do some work, and then produce some more messages in a late bound fashion, then it's a useful definition. But if you think of it as classes, where classes that represent a particular row in a database, then it's not particularly helpful for trying to model actual real-world properties. So those are the two barriers to entry. Actually, people get trained for years and years and years. Like all the way through university now, computer science graduates get trained that object-oriented programming is classes with inheritance, with parametric polymorphism.
Cars and tanks and dogs and cats and fruits and bananas.
So you get to write event-free systems. Everyone's trained for this. Bring it on. Cat inherits dog and that's very wrong.
And the other thing about the messages is a log is equivalent to a queue where you wrote everything down in order. So a message queue and an event log is just semantically a log of events or a queue of events, same thing. But it's persisted, so it's repeatable and durable. You had another question?
Yeah, actually I got two questions. Maybe one is related to the other one. I'm trying to wrap my head around versioning and data structures over time.
Sure.
How does one manage V1, V2, V3?
V1, V2, okay. So the first thing you're going to do, so that's actually answered in a number of different places. So one, by ensuring we're not coupling commands or private state to our persistence, we're going to allow our decisions, our state machines, to version on the same events, right? So the exact same business events are can be running different machines, if you will. So different services or different versions of the same service.
Are the machines then also persistent?
No, those are code. So they're brought up, they're code, they're run, they produce a state that you don't know what it, that's private to it. They produce another event that's written down publicly in their stream and they go away. So, and that's what we're trying to avoid. We're trying to avoid things that need that particular set of code to be understood. So the next thing we do is we want these events to be business events because business events are not going to change as fast as other things. And then we can also project them into new views, right, as the business request changes. However, we're then going to find those events are going to change. So we've protected ourselves two ways, but they are going to change. They are going to need to be versioned. So the first thing we do is we use a weak schema. We don't want to serialize the events as binary serialization. We want to use something like JSON, right? Because if you go back to like a relational table, if I add a new column and I give it a default, I can keep on extending that table. And other things that are reading it that are older don't break. So with a weak schema, we can do that. I can add a new field that's new, right? And not break old things. I can stop using an existing field, right? So that's the second basic way to do it, is that weak schema. And if you can't make a change with that weak schema, you probably have a new event. So then you actually can go back and reiterate. Your break glass approach to versioning is you actually just take a stream, create a transformer for your update, and you write out a new stream. Right, that's like this is all wrong, yeah. So you get a new queue, and you write it out. Okay. The other thing that helps out with that is plan your data retention strategies. So you should do this with all of your databases, right? Anything. But here, if I actually plan to roll the books and do a cutover on a business schedule like the end of the year, I can take those old events, put them in an archive system, right? And then I can have an archive viewer on that if they need it, but it's not part of my live system. It's easier to maintain. I can save money on storage. I'm going to have different SLAs. and probably even different use cases. And that means I only have to have 2 or 3 versions of the events in that. I don't have this long tail of 10 years of changes that everything's got to understand. There are more advanced approaches using checkpoints and but you don't get into that. Read Greg's book. It's on LeanPub, versioning event source systems.
Versioning an event source system is basically the answer to all of those questions. It has
Yeah.
like 50 different strategies for dealing with these things.
It's complicated.
Yeah, the patterns I talk about are the first ones in the book.
And another question is about, in Europe there's something called GDPR.
Yes.
Because we're storing the whole history, how do we manage that?
We had 2 options generally on that. The first is key shredding, which is you take the data you want to be able to get rid of and you encrypt it.
Yeah.
And then when they say I want to be forgotten, you destroy the key. So all the data is there, it's now just random bytes.
It's still there, but it's not value.
Not accessible. Your company can no longer gain access to it. Some people have problems with that. One of the ways to deal with that is you separate that data out. So you have your core customer identifier, and then the private data or the identity data is stored separately. So you can keep your record of I had this customer, these things happened, when they want to be forgotten, I don't know who that was.
You just keep the key. Basically.
Yeah.
The key in the
patent name, it's actually in Patents of Enterprise Application Architecture by Martin Fowler, which is called claim check pattern.
Yep.
So instead of storing the data that you might need to delete, you store a key for it, and then you have some ability to look up that data by the key,
Yep.
and you accept that if the user withdraws consent, then you have to go delete that data.
Right.
My personal preference is the key shredding one, because it's just neater.
Yeah.
But it's actually not been tested in court, so
Right.
So
And the
you
last
can get it safely.
And the last thing to remember is not all personal data is subject to deletion. If you're keeping a record of someone like a stockbroker who's making trades, you're keeping that data not because they consent, but because of regulation.
Yeah,
So
regulation
not
always
all
wins,
of the user data is subject to that.
Thank you.
I guess it's a question around the approach to solving the problem around event sourcing. There's a few different tools out there, especially on the JVM. I think they've got Lagom and the Axon framework, but they approach it from a different angle. They almost persist agnostic, whereas Event Store starts with the database.
So Event Store is a database. It's
Yeah.
a framework for building an application.
Yeah.
So it has the interface of Event Store is put this event on the stream if the version number hasn't changed since you last tried writing, and read these events and subscribe to these
Right.
events. There is some more to it than that, but that's the most part. It doesn't have any opinion about how you build your application, what
Right.
technology, whether you use a functional style, whether you use an object-oriented style, whether you really whether you do it event sourcing. Actually, it has no opinions on that. If you start from a framework approach, you will get framework problems. So it will work until it doesn't, and then you are fucked.
You really want a library. Something where
Libraries are definitely the way to go.
you're
So-
pulling in tools you need, not using the framework to do what you want to do. And Event Store will run on Linux just fine, gives you an endpoint, there's a Java client, right? And you want something that lets you pull what you need out and not starting with a framework. Because with a framework, a lot of these decisions on how to do things are made for you. And very honestly, how I would set up event sourcing for a line of business application and how I would set up event sourcing for a high performance application in like medical imaging or trading, very different. Entirely different frameworks, approaches, setups, because they don't work for each other. One of them, I want something that's simple, it's going to use the latest tools, my developer is going to be able to deal with. The other one, it's like, no, I want to control every thread. I want to do this, I want to do that. And frameworks make all these choices. They don't just make one, they have to make them all.
There's the extension of that, which is like event sourcing at its core is really simple, right? It's a left fold over some data. Like, do you want a framework for that? Probably not.
Right.
Like, your language probably has a dot fold function
Right.
in it. It was written since 2001. So actually, you don't need it. Like fundamentally, introducing a framework is always more complicated than not introducing a framework for almost every. By that I don't mean like a .NET framework, like a runtime, but I mean like adopting Spring is always more complicated than not adopting Spring, and that's an example that both .NET and Java users can agree on.
So
Java became known as a DSL for converting XML into backtraces because of Spring. And, but fundamentally, it's a really simple problem, and it's a fold, and it's writing to a database, and it's somehow exposing that to a user using like probably an HTTP API in 2007. What year again? 2009. Fundamentally, you don't need anything to do that for you. Now, where it is useful is where you can have a bunch of the work done for you, and for that, there are a bunch of choices. There's some great libraries that actually I didn't pause on. Well, you're on the .NET platform or Java?
Java.
.NET.
Oh, .NET. Okay.
In that case, there are like 5 or 6 high-quality libraries rather than frameworks that you can choose from that do the heavy lifting for you without making important decisions for you. One of my favorites is called Aggregate Source.
Yep.
There's a guy called Yves Raymond in Belgium. Did a lot of work on that. Contributed to it a while back. There's probably 10 others as well, all of which make slightly different decisions, and you interact with them in a slightly different way, and you can evaluate and choose them. But the important thing is to make sure you're in control of the entry point of the application, the entry point per request, and the threading model of the application. So there's a bunch of them that use things like actor models, and you probably don't want those because you have no control over where anything happens, and no ability to make trade-offs to scale things.
So I wrote a framework that I use in my workshops to teach event sourcing in about a weekend, right? So it's not a lot of code. I'm one of the original members of a framework, React to Domain, but that's very targeted for high performance, and it makes a bunch of decisions about SATA. But I don't know what would be appropriate for what you're doing. If you want something more object-oriented, aggregate source is going to be way better. So
yeah, I was just asking about the approach. It's completely different to a framework. Framework might be too prescriptive, as you said, in certain circumstances. I've worked in 3 different event sourcing systems and written it 3 different times.
Right, because it's not that hard.
Yeah.
You make like 10 or 15 decisions and you're done.
Yeah.
Actually, I have a post on my blog, and it turns out it's basically the last post on my blog is, although I say I have a blog, I actually posted on it for the last time in 2014. That doesn't go, which is not the most expressive language in the world, and it's seriously just like 50 lines of code to get. So, not that hard.
Question, all right?
Curious, with working with large data sources,
Yep.
do you have any tips on archiving the data or optimizing for fast reading?
So cache. So one of the things that we get about from an immutable log is we solve one of the hard problems in computer science, cache invalidation, right? The state at position 9 is never going to change. We might be stale, but we're never going to be wrong, right? And if I have, a billion events, we have customers that have data sets this size, I'm not going to be using the tail of that very often. So what I want to do is I want to use independently running collectors that are running all the time, producing targeted, consumable views of the data, and then storing those either in a memory cache or in document, graph, or relational database for queries. One of the keys about those is always include in your state the position, your checkpoint. That way you know where it's at, right? And you know whether it's valid or whether or not something's new. So whenever you write out your table, write the checkpoint of when that table update is equivalent to in your primary source. Okay. The other thing that's really good about that, once you start caching and distributing, the fact that we've got a simple incrementing number on our position is wonderful for message out of order detection, right? If I'm on 5 and I get 7, I know I missed 6.
So right? It has to be predictable, the ID.
Right. And so as you build up caches and you have these systems out there, you want to know where you're at, you can ignore something with a lower sequence number, right? And if you do need to bring together separate streams where you don't have the global ordering, then use vector clocks. And that's just taking the position in each one of the streams and creating them as a tuple, right? 2 or 3 part for each one. And then that gives your position in the cache.
Vector clocking. Okay.
Right?
Thank you.
Does Event Store support asset transactions?
Yeah.
Yes.
Oh, sorry, that's all I want.
Yeah.
Yes or no? Awesome.
Actually, so let me explain that.
Yeah.
So yes, it does. So you can atomically, consistently in an isolated and durable fashion, append one or more events to a given stream.
Right.
You cannot do it across more than one stream. So you can't write to order A and order B in a transactionally consistent manner. But you also probably don't want to do that because
Right.
the point of a stream is it's the consistency boundaries of which also it's a transactional one. Technically, we could allow you to do that, but from an API perspective, we don't want to because it prevents you from being able to horizontally scale in the future. So it's an artificial limitation that we put in there to prevent you doing bad things. But yes, you can within the stream.
Yeah,
Right.
I think it's important, at least on a stream level.
On a stream level, it's critical.
Right, no,
you
it's-
can't do
I
it
just thought, if you're using
Right.
Mongo, you'd be stuffed. You'd have to go write it all yourself.
Right, exactly. And
Actually,
that's why.
there's tools to write it yourself. So there's one, there's an aspect of it which is, especially long-running transactions are a big problem. So there's no reason in principle with, because of the data model of Event Store, you can, in principle, there's no reason you should do this, but you can, in principle, open a transaction today, write an event to it. Write another event in 5 years' time and commit the transaction. If the state of the stream is still correct in 5 years' time, such that it should succeed, it will succeed because of the data.
Makes sense.
You should not do that because that's stupid.
Yeah.
Actually, we probably shouldn't allow you to do it. But there's also no compelling reason to stop people doing all bad things. Just do really bad.
Right. And that's one of the reasons why I said pick a database, because you need that asset commits. And then the stream boundaries are just good for your application and good for performance. And if you can commit more than one event together on a stream, do that because the performance is just better.
Do you have any practical advice, especially for larger teams working on event source systems, how to ensure that events, say, develop time do not get tampered with over time, that somebody accidentally removes a property before?
How, what gets,
Once,
what's that?
So I think the question
No, I just didn't hear it.
So I think the question is, how do you ensure in a large team that people don't modify the definitions of events when they shouldn't?
All right. So there's a new formalization of an old technique called event modeling that I've been using. Actually, I got taught by Greg when I learned to do it. And it's like event storming, but you create a durable model with all the data in it as a team living document to document the commands, events, and views of your system. And that becomes a template for what you're building in the system. So you make sure that document is isomorphic. And so changes happen in the document first with version control and conversations. So before it goes into the code. So you start off with your event storming, you do a formal blueprint of your system, get all of your, because effectively your events and your commands and your views become the public or the internal API or schema of your system. It's your ER diagram.
There's actually another thing